You used a microwave today. The backstory starts with a melted candy bar in a radar lab. In 1945, engineer Percy Spencer stood near an active magnetron, the microwave-generating tube used in wartime radar, and noticed chocolate in his pocket had softened. He did not ignore the anomaly. He ran quick tests. Popcorn kernels popped. An egg ruptured. The observation was consistent with microwave energy heating water-rich materials. The next step was not a public presentation. It was controlled work, notes, patents, and prototypes. Raytheon documented the conditions, constrained the energy inside a metal cavity, and added a waveguide to direct power. Engineers had to turn a laboratory curiosity into a repeatable process. That meant making inputs, outputs, and safety measurable. They addressed uneven heating with a mode stirrer to scramble standing waves and, later, with turntables that physically moved food through varying field intensities. These changes were not decorative. They targeted a concrete failure mode, cold centers next to overheated edges. The first commercial unit arrived in 1947. It was called the Radarange. It was tall, heavy, and water-cooled. It worked, and it did not fit a normal kitchen. Restaurants, ships, and institutional kitchens could justify the footprint and plumbing. Households could not. This was not a dead end. It was a clear signal that physics was no longer the constraint. Form factor, cost, and installation were. In 1955, Tappan released a built-in home model. It solved one barrier by integrating into cabinetry, but it left two others in place: high price and unfamiliar use cases, a four-figure price in mid-century dollars. Limited adoption. At the same time, the device did not replace ovens or ranges. It performed a different set of tasks: fast reheating, rapid defrosting, and quick steaming. Early consumer value was narrow. Narrow value is still value when it removes a frequent pain point. That is how a category begins. The 1960s brought incremental engineering that solved practical issues. Manufacturers such as Litton altered cavity geometry to reduce arcing. Door latches and seals were improved, so units stayed off when open and stayed within leakage limits when closed. Designers hardened circuits so the magnetron could survive abuse, including operation with no load. As factories produced more magnetrons, yields improved and costs decreased. Power supplies and cooling systems became smaller and more reliable. Cabinets shrank from an appliance the size of furniture to one that could sit on a countertop and plug into a standard outlet. In 1967, Amana, then owned by Raytheon, released a compact countertop model with a price point many middle-class households could consider. The change was not only cost, it was context. The unit fit on a counter. It did not need special wiring or plumbing. Retailers could demonstrate it. Demonstrations were simple and effective. Heat a plate of leftovers in a minute, defrost a frozen cut of meat to a usable state, reheat coffee quickly. The proposition was clear: save time on routine tasks. Public concern about safety was a serious constraint. The term radiation created understandable hesitation. Engineers responded with interlocks that cut power when the door was not securely latched, with seals that kept emissions far below regulatory limits, and with labeling that warned against common misuse. Communication emphasized that microwaves are non-ionizing. They heat water molecules by causing them to rotate, but do not ionize atoms or damage DNA. The best argument, however, was consistent field performance. Units did not run with the door open. Doors did not loosen and leak. Cavities did not spark when used with appropriate containers. When devices behave predictably at home and at work, fear declines. Adoption did not jump from zero to ubiquity. It followed a curve. After the countertop release, restaurants and office break rooms used microwaves for specific tasks. Landlords and builders began to include them. Packaging designers created microwave-safe materials and coatings to improve texture. Cookbooks added timing tables and basic rules. By the early 1970s, shipments were increasing. Around the mid-1970s, annual sales passed 1 million units. In the 1980s, a majority of U.S. households owned one. The device moved from early niche to household standard. Notice the chain of events. Wartime research funded magnetrons and associated materials science. An engineer with domain knowledge noticed an unexpected effect and tested it. A company documented and patented the mechanism. Early deployments targeted non-consumer environments that could absorb cost and bulk. Design changes improved reliability and safety. Manufacturing scale reduced price. Retail demonstrations translated the value into everyday terms. This sequence, observation, mechanism, repeatability, usability, reliability, affordability, and distribution, shows up in many successful technologies. It is also useful to note what the microwave did not do. It did not replace baking, broiling, or searing. It became the best tool for specific jobs and stayed within those boundaries. That clarity helped adoption. Claims that a device replaces all prior tools usually fail. Proof that a device performs a small set of frequent tasks faster usually succeeds. Later additions such as browning elements, grills, and convection modes extended capability, but the core remained speed for reheating, defrosting, and steaming. Usability mattered. Early owners overcooked eggs and dried out meat. Documentation evolved from technical language to simple rules. Cover dishes to retain steam, stir once during heating, pierce skins, use microwave-safe containers, allow standing time for carryover heat. Interfaces shifted from power dials and time wheels to presets. A popcorn control is not just a label. It encodes assumptions about mass and moisture to produce a consistent result without calculations. These adjustments moved the device from a specialized appliance to a common kitchen tool. If you build products, 3 practical points follow. First, treat anomalies as leads. Many people discard unusual data. Effective teams test one more time under controlled conditions. Second, ship a form factor that fits the environment of the first real customer, even if it is not the final market. A water-cooled unit makes sense in a commercial kitchen long before a countertop unit is viable at home. Third, remove adoption blockers in order: safety, reliability, cost. You will not reach wide distribution if early units fail, scare users, or are priced beyond the problem they solve. Policy and public investment play a background role. Large research programs aimed at military goals created capabilities in vacuum tubes, ceramics, and manufacturing that private firms repurposed. The path from radar hardware to a household appliance was not linear, but it was traceable. Similar spillovers appear today in areas such as specialized compute, energy storage, and laboratory automation. Public research often creates technical capacity. Private development turns that capacity into specific products when costs, form factors, and use cases align. The adoption story also shows the importance of predictable outcomes. The microwave grew because it produced the same result faster than the status quo, and because the result was good enough for the task. The explanation was easy to repeat. This box heats food quickly and safely. Word of mouth was based on performance, not novelty. If you want a new tool to spread, identify a common task, reduce time and effort, and ensure reliable results with minimal instruction. Revisit the start of this story. The critical step was not a dramatic insight. It was a small choice. Do not discard an odd observation. Test it. After that, progress depended on standard work. Measure, redesign, test again, and reduce manufacturing variation. Choose early customers who benefit even when the product is large or expensive. Reduce size and cost as the technology matures. Write instructions people can follow without training. Remove obvious failure modes, such as door misalignment or operation without load. Make the value legible at a glance. Repeat. The same evaluation applies to technologies you see today. When a lab result appears in the news, ask concrete questions. What job does this perform better than the current tool? Can the mechanism be contained in a safe, repeatable, affordable package? Who will tolerate rough edges first? Industry, institutions, or consumers? Which engineering tasks stand between a demonstration and a routine habit? Answers to those questions predict which findings will become common and which will remain demonstrations. One final point. Many effective technologies originate in other fields. Radar hardware became a kitchen appliance because people with the right skills transferred knowledge and then handled details until the device fit daily life. The challenging work is not noticing an effect. The challenging work is moving a controlled result into everyday use by removing friction, documenting limits, and aligning price with value. That process produced a microwave on your counter? The same process is available to anyone building with today's tools.